Hey everyone, welcome back to Abstract Algebra 1. This will be part B of Lecture 8. So we had just finished with Cayley's theorem, right? So we just saw Cayley's theorem. Cayley's theorem is a powerful theorem that said that for any group that you can think of, is going to be isomorphic to some permutation group. So for any group G, there exists an isomorphism from G to a permutation group. Right, so we just saw that. We proved it, and then we did an example. In the course of the proof, we uncovered the idea of the left regular representation of a group, and then we did an example of that with U12. Okay. What we want to do in the last section here is talk about some of the properties of isomorphisms. Okay, so we're going to talk about properties. We're going to kind of break this into two sections. Right, we're going to talk first about properties of isomorphisms acting on elements. Properties of isomorphisms acting on elements. And after we discuss this one, we're going to get into properties of isomorphisms acting on groups. Right, they're different categories of action. Right, so we're going to start with what are some of the properties of isomorphisms when they're acting on elements inside of a group. Okay, so we're going to let phi be an isomorphism. From G onto a group G bar. Okay, then we got 5 key properties here. 5 key properties. The first one says that phi carries the identity in G to the identity in G bar. Now I'm going to denote the identity in G bar as E bar. Okay, just for our notes. Right now, most of these properties are going to be very straightforward. If you take seriously the idea that groups that are isomorphic have the same structure, right? So this one should be relatively obvious given the definition of the isomorphism. E in G ought to be mapped to E in G bar if the structures are preserved, and indeed they are. This one, the next one, says that for all integers n and for all elements of the group, phi of a to the nth power is equal to phi of a all raised to the nth power. Right, so if I raise a to the nth power and then map it, I'm going to get the same result as if I map a and then raise the result to the nth power. Again, a consequence of the groups being isomorphic and having the exact same structure. Okay. The third property, so for all A and B in a group, A and B commute if and only if they commute under the isomorphism. So phi of A, phi of B equals phi of B, phi of A, right? So if they commute over here, they must commute over here. If they commute over here, they must commute over here. Again, a consequence of the two groups having identical structure. Okay. Item 4. So the order of an element A in G is going to be equal to its counterpart in G bar. Right, so if the order of an element A is equal to n, then its counterpart in G bar will have the same order. And a lot of this is kind of a laundry list of what does it mean that the two groups are structurally identical. It means every element has the same order. It means elements that commute must commute in both places. It means that this is preserved. It means identities are mapped to one another. Okay, and then the last one we'll mention here, and there's more, but we'll stop here. For a fixed k integer and a fixed element in the group B, right? So I've got some group element that I grab, and I've got some k integer. The equation x to the k equals b has the same number of solutions in G as x to the k equals phi b has in G bar. Okay, so this one here is a little different, right? This one is a little bit different. This last property we'll see is going to be extremely useful. Well, it's extremely useful for showing that two groups are not isomorphic, right? So if you can find an example, if you've got two candidate groups, you want to know if they're isomorphic, this might be something to check first. Are there any examples where this fails? Right, so property 5 is useful in showing when two groups are not isomorphic. Okay, so an example would be, let's do a quick example just to kind of solidify that a little bit. If we consider the complex numbers absent the origin and the real numbers absent the origin, then so we removed 0 from both of these, right? So these are both groups under multiplication. But if you think about x to the 4th equals 1, right, as an equation, right, this has, how many solutions does this have in the complex number system? 4 solutions in C. This has 2 solutions in R. Okay, so this is a counterexample of this property 5 up here, right? So the implication is that C star is not isomorphic to R star, meaning you're never going to find an isomorphism between these two groups. Okay, so that's kind of the value of 5. Well, it's interesting in other ways, and it has other values as well, but that's one of the main values. Okay, let's come back to some of these, and let's prove a handful. I'm going to prove 1 and 4, right? These others can be done as well. Not super tricky, but let's just take a look at 1 and 4. Start with part 1. So for part 1, right, we need to show that phi of E equals E bar, basically, right, where E is the identity in G and E bar is the identity in G bar. Well, okay, so let's note first that E equals E times E, right? E, the identity can be applied to itself and it's equal to itself, right? Right, so that being the case, then we have the first thing that we need is phi of E equals phi of EE equals phi of E, phi of E. Right, so this is just the fact that, we're assuming that phi is an isomorphism, right? So if that's the case, then phi of E equals phi of EE equals phi of E times phi of E, right? So that whole thing works out. That's just a consequence of isomorphism and the fact that E has this special property. Okay. All right. So note second that phi of E, whatever it happens to be, is an element in G bar, right? G bar is a group, it's closed, right? And so we have closure in G bar. And so we get, from there we get item 2, which we need, which is that phi of E is equal to E bar times phi of E. Right? Remember, this is just an element of G and, of G bar. Phi of E is in G bar. E bar is the identity in G bar. And so obviously this is true. You're taking something in G bar, multiplying it by the identity, right? So this works out, okay? And so between 1 and 2, we can basically get what we need. So we'll start with this. Phi of E times phi of E equals phi of E, right? That's right here. And then we know that phi of E is equal to E bar phi of E. All right. All right, so we don't need this middle piece here. So let's just kind of simplify this a little bit. Let's see if you can see how this was going to work out. Well, these will just cancel right off, won't they? So we get exactly what we want. Okay, so the identities map. E is mapped to E bar under phi. Okay, so that's part 1. Now let's look at part 4. What was part 4 again? Part 4 said that the order of A in G is equal to the order of phi of A in G bar. Can we prove this? Sure. Okay, so this is going to use property 1 and 2. So technically speaking, we've proven part 1, but to make this truly rigorous, you'd have to go back and prove part 2. But by property 1, what do we get? We get phi of A to the n equals phi of E. That's not the property 1 piece. This is the property 1 piece. Right, so this is just the order, right? So if I raise A to the n power, let's say the order is n. Well, I should say that up front. Let me say that the order of A is equal to n. Okay, so that means phi of A to the n is equal to phi of E, which is equal to E bar. So this is the property 1 piece here in particular right here. Okay, and now we're going to pull in property 2 here, and so let me remind you of what property 2 says. Property 2 says that phi of A to the n equals phi of A all raised to the n. So we're going to use that next. And so we're going to combine these two, basically, right? And so here I've got phi of A raised to the nth power. I know that's equal to phi of A to the n. And then I know that that's equal to, they're both equal to E bar. So this guy's equal to E bar in particular. Okay, so both of these are equal to E bar, and this guy, this is the order. This implies that the order of phi of A is equal to n, right, because of the n. And you also have the same thing here. The order of A is equal to n because this guy goes to E, right? Well, we assume the order of A is n. Right, so this is equal to this, which is what we needed to show. Okay, so there we go. Perfect. We've got property 1, and we proved property 4. Again, the others are not any harder, really. They're actually kind of comparable. All right. So that was kind of a list of properties of isomorphisms acting on elements. Let's talk next about properties of isomorphisms acting on groups. Okay, so the theorem is as follows. Suppose that phi is an isomorphism. Suppose phi is an isomorphism from a group G onto a group G bar. Then, first, G is abelian if and only if G bar is abelian. Right, so this aligns with the first or one of the items. Which one was it? This aligns with item 3 from the previous theorem, where we said AB equals BA if phi A, phi B equals phi B, phi A. Right, so if the two elements commute in one, they have to commute in the other. Well, just take that to its extreme. If every element in G commutes, then every element in G bar also commutes, and vice versa. So this one almost follows immediately. The second thing is G is cyclic if and only if G bar is cyclic, right? Again, most of these properties are just going to be natural consequences of taking the idea that isomorphic groups have the same structure very seriously, right? So if G is a cyclic group, then the group that it's isomorphic to that has the exact same structure as it must also be cyclic. Okay. This one may not be, well, no, this, hopefully if you think about phi as a mapping, then if phi is an isomorphism from G to G bar, then phi inverse is an isomorphism from G bar onto G, right? We know that functions that are one-to-one and onto have inverses, and so this is just saying that, hey, the isomorphism runs both directions, right? If you've got an isomorphism from G to G bar, then you also have an isomorphism from G bar onto G. Okay, very good. And then the last one we'll mention here says that if K is a subgroup, it's a subgroup of G, then phi of K, which would be like the image of K under phi, is equal, phi of K, we can define it as phi of K such that K is in the subgroup K. Right, so if K is a subgroup of G, then this set here of all the elements, where you take something out of the subgroup K and you map it under phi, right? So this set of elements is a subgroup of G bar. And that should be obvious as well, right? So the K is a subgroup of G means it's closed. Every element in K maps when you operate on them, they stay within K. Well, it's going to be the same thing over here, right? If you take everything in K and you map it over into G bar, then you get a new subgroup in G bar. Okay, so these are some of the key properties of isomorphisms acting on a group. Okay, all right, and again, most of these, with the exception of maybe 3, 1, 2, and 4 are all just obvious consequences of G and G bar having the same structure. 3 is something that shouldn't be surprising either if you take seriously the idea that phi is a function, a one-to-one and onto function. It must have an inverse, and so that inverse defines an isomorphism in the opposite direction. Okay, definition. So there are some kinds of isomorphisms that are used so commonly they have their own kind of name, and that's what this one is. This is the definition of an automorphism. So an isomorphism from a group G onto itself is called an automorphism. And I should say of G. Right? So it's an automorphism of G. Right, so basically an isomorphism from G to itself. Right? So, and it's clear that every group is isomorphic to itself. You just have to come up with some isomorphism. It's real easy to do that. You can always just use like an identity isomorphism. Okay, let's do an example that isn't kind of like a trivial one here. Let's let phi from C to C, right, complex numbers to complex numbers, be defined as phi of A plus BI equals A minus BI. So phi, as defined here, is an automorphism. It's an automorphism of the group C under addition. One-to-one and onto are obvious. How about operation preservation? It's somewhat easy to do, but let's just outline this. So if I take A plus BI plus C plus DI, these are obviously elements in C, and I add them together, what I can see is that this is going to be equal to phi of A plus C plus B plus DI, which under phi is equal to A plus C minus B plus DI, right? Then I can just rearrange that, and I get A minus BI plus C minus DI, which of course is phi of A plus BI plus phi of C plus DI, right? So you get what you need there. And so this is an example of an automorphism. And there's lots and lots of examples of these. They're very easy to come up with. Another example would be this one. This would be a familiar example probably. So we'll let R2, which we know is the ordered pairs of real numbers, then phi of AB, if we define that to be, just let's flip them over. So phi of AB equals BA, then this is an automorphism. This is an automorphism of R2 under addition. Right, this is basically a reflection, isn't it? It kind of flips everything. The x component becomes the y component becomes the x component. Okay. All right. Very good. Very good. All right, so these are examples of automorphisms. Again, automorphisms are just isomorphisms, but they are from a group onto itself. Okay. Here's a special kind of automorphism. Let's let G be a group and let A be any element in G. Then the function phi sub A of x equals A times x times A inverse is called the inner automorphism. It's the inner automorphism of G induced by A. Okay, so this is a special kind of automorphism that will come up a lot. And so basically what this says is, hey, I can define an automorphism in this way. I can just pick an A in G, and I can multiply every element in G by A and A inverse. Okay, and when I do that, that's going to map onto back onto G, and so it becomes an automorphism, and we call it, it's a special one called the inner automorphism. Let's see an example of this. Okay, we're going to run this example out of D4 again, from D4, the dihedral group. Now remember the dihedral group, it's R0, R90, R180, R270, and then you've got some flips. So horizontal flip, vertical flip, and 2 diagonal flips. All right, that's D4. So let's kind of go through and see what the inner automorphism of D4 induced by a 90-degree rotation looks like. The inner automorphism on D4 induced by R90. Right, that's what we're interested in here. So let's see what happens. So R0, it's a 0-degree rotation. The way to calculate what this automorphism does with this element is to take R90 times R0 times R90 inverse. Right, now this is hopefully, like, this is such a nice physical group to think about. So you start with a negative 90-degree rotation, and then you rotate 0 degrees, and then you rotate positive 90 degrees. And so, of course, this is equal to R0. You've not moved at all. Right? You can do the same thing for R90. Right? So this would be R90 applied to R90 applied to R90 inverse. So you start with a negative 90-degree rotation, and you then rotate 90 degrees, and then you rotate a further 90 degrees. And so how much have you rotated in total? 90 degrees. Right, I'll skip R180 and R270 because you'll see that they are the same thing. Well, I'll write them. So the rotations are very well behaved. They just kind of map to themselves. Okay, what about the flips? So what about H? What happens with H? Well, H under this mapping is going to be a 90-degree rotation followed by a horizontal flip H, followed by a negative 90-degree rotation. What does that actually look like? So let's draw a square here. Right, so if I have A, B, C, D. So first I'm going to do a 90-degree rotation, and I might be doing this in the reverse order. It doesn't matter, you get the same answer both ways. And if I do the 90-degree rotation, then everything kind of shifts in the 90 degrees, right? So this becomes B, C, let's see here. Wait. Hold on a second. So 90-degree rotation. Yeah, so B, C, D, A. Okay. And then I do a horizontal flip. Actually, I need to do this in the right order. I apologize. So if I start with my A, B, C, D, right? And then I do R90 inverse. That means we're going this direction, right? So that gets me C, B, A, D. Okay, then I'm going to do a horizontal flip. So that means I'm going to flip it like this. And so I get D, C, A, B, right? This is H. And then I'm going to do a 90-degree rotation. Okay, and so that means I get A goes down, B goes over, C goes up, D goes over. Okay, and so what I've really done here is a vertical, right? So if I start here and I go straight over to here, you can see that B and C switch places and D and A switch places. So this was really just a vertical flip. So H actually maps onto V under this, inside of this this inner automorphism. R90, this inner automorphism of D4 induced by R90 takes H and maps it to V. And it turns out you can confirm this doing the same kind of going through these. You can see that V goes to H. D and D prime also switch spots. D goes to D prime. These are the main diagonal flip and an off diagonal flip, alternate diagonal flip. And then this would be, of course, D prime goes to D. And so this is an example of an inner automorphism of a well-known group D4 that we've been playing with for a while. All right. Okay. Very good. All right, one more theorem, and then we will call it quits. This has been a very long section. Some of these sections are very, very long and challenging. The last theorem here. The last theorem says that the set of automorphisms of a group and the set of inner automorphisms of a group are both groups under function composition. So aught G, this is the set of all automorphisms of the group G, and in G, this is the set of all inner automorphisms of G, are both groups under function composition. Right. So these are groups under function composition, right? So remember aught G, all automorphisms of G. In G, all inner automorphisms of G. Right. These are both groups. Right? These are both groups. All right. So if you take, so remember, an automorphism is an isomorphism from G to itself. If you take the set of all such isomorphisms from G to itself, all such automorphisms, then you get a group under function composition. Meaning you get closure, you get associativity, you get inverses, and you get identities. The same is true for the inner automorphisms of G. Right? Now the inner automorphisms of G are actually really easy to find. So if a group G is E, A, B, C, so on, then the inner automorphisms of G are really easy to find. They're just, however you want to denote the function. It's the function with E, it's the function with A, the function with B, and so on. So these are really easy to find. Some of these elements, of course, could be, duplicative, right? Phi of A may be the same as phi of B, but in general, it's easy to identify all the inner automorphisms of G, right? It's really just a case of you have to go through and make sure you figure out which ones are actually unique, right? But the automorphisms of G, on the other hand, can be really involved and difficult to identify. So in G is easy to find, but automorphisms of G, the group, can be hard to find, hard to identify. Okay. All right, I think we'll leave it there. That's a lot of material, I know, but that's everything we need from isomorphisms, I think. So next time, the next lecture we'll discuss cosets, and we'll get into one of the most important and most beautiful theorems from group theory. That's typically referred to as Lagrange's theorem. All right, until then, take care.